Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were talking about gravitational waves and their discovery. When they were discovered back in 2016, it is a culmination of over 40 to 50 years of work with the LIGO observatories being built, and the people who devised it and supported it through the decades got the Nobel Prize for the initial discoveries. Well, since the initial discovery in September of 2016, there have been a grand total of six other, as of this particular time, 6 other gravitational wave sightings that have occurred, and we're going to talk about the most recent of those, the last one that was discovered, and it's the most important. So again, we're looking at the gravitational wave spectrum, and the spectrum here shows that gravitational waves themselves are predicted by general relativity, and the ones that are currently doable are with the terrestrial interferometers, which would arise from very rotating neutron stars that have little lumps on them, and that would make them star things, and also supernovae should be these things that they see. Also, we should see compact binaries such as binary black holes, which is the dominant number. The first 5 were medium-sized black holes, meaning a few tens of solar masses as they combine. But what if 2 neutron stars collide? Neutron stars, of course, are very massive objects that can compress to extremely small sizes. Most neutron stars are between, say, 1 and 3 times the mass of the Sun, and that whole amount of mass has been compressed down to something a few miles or a few kilometers in diameter. They're very, very, very tiny. It's extraordinarily massive. And in my neutron stars video, I discussed exactly the interior structure of these neutron stars and how incredibly tiny it is. But basically, there's zero space between the individual nuclei in the neutron star. You come up with these wild phases of mapping that generate individual nuclei. All of a sudden, the interior of the neutron star is effectively one big experience. Importantly, neutron stars have the property of being a pulsar. One of the important properties is that they shrink. The magnetic field of the star itself gets more intense because the material that makes the magnetic field is important. So since it's not going away, as the object shrinks, the intensity of the magnetic field increases radically. It increases so much that the magnetic field itself can accelerate particles to nearly the speed of light. And as they get ejected out the holes, and it also creates hotspots on the magnetic poles of the neutron star. And if the magnetic poles are not aligned with a spin axis, then they pulsar, and the beams of light come from a neutron star along its polar magnetic field axis, because as electrons go spiral in the magnetic field at nearly the speed of light, synchrotron radiation and radio, as well as X-ray light that we see these as X-ray or gamma ray pulsars. So a pulsar is an incredibly important element of the neutron star experience. And as pulsars spin down and get slower and slower, they fade away. So we should expect to see a large number of neutron stars throughout our Milky Way. And their effects are very important, as we'll see soon. Back in 1974, Russell Allen Hulse and Joseph Hooton Taylor discovered a binary pulsar. 2 neutron stars orbiting each other, both of them pulsars. And their discovery earned them the Nobel Prize in Physics in 1993. For a reason we'll discuss, and that's subject of this video, the same thing, in just a second. It's called the Hulse and Taylor pulsar binary, and each of these neutron stars, the initial neutron star was found to be rotating 17 times a second on its axis, and they eventually did, with follow-up observations, were able to determine that it was a binary neutron star, and they used the Arecibo Observatory that you see here, which is located in Puerto Rico. What they did that got them the Nobel Prize, though, is that since they discovered it was a binary pulsar, they timed the radio pulses for a long time and noticed that there was this incredible systematic variation in the arrival time of the pulses. They changed in a very smooth and repetitive manner, and their normal period is about 7 3/4 hours, and this variation was happening if that the variations in this binary, the initial binary the initial pulsar they found, had a variation that changed smoothly. And that's if it was in an orbit around another binary, another pulsar. And that's the only way they found that. So he said, oh, this thing is changing. So if it's doing that, it's just in the same way that we would find a binary star. So we might find a spectroscopic binary. And instead of finding a spectroscopic binary, we found a pulsar binary. So what they discovered by looking at the variations between them is that the pulsar they orbit each other in about 3 light seconds, with a diameter of about 3 light seconds. And that's about 2/3 the diameter of the sun. So remember, 100 Earths fit across the sun. So this would be about 60 or 70 or 60 or so Earth diameters between these two pulsars. And each of the pulsars is about the size of a big island, such as Manhattan Island or so. So they can see each other in the sky in a certain way. They'd be very, very, very bright in X-rays. And they were able to determine that the masses of each of these pulsars was about 1 and 1.4 times the mass of the sun. What they then showed was that the pulsars' orbit around each other was gradually contracting. And as they showed that it was gradually contracting, that meant the period of the pulsars were shifting. And as they shifted, the periodic shift accumulated. So what they found is that the pulsar timing, when they got the actual pulses from it, was getting closer and closer and closer together. And that's as a result of the two pulsars approaching each other. So why do they approach each other? Because they emit gravitational waves. So this graph is showing you the cumulative period shift of the orbit of the two pulsars as a function of time. And it takes years to watch it. And each of those red dots is a data point. The blue line that fits them is the prediction of general relativity if they're emitting gravitational waves. And that's how they're losing energy such that they're coming together. And notice how the prediction of gravitational wave emission exactly matches the dots of the data. So that's what earned them the Nobel Prize in 1993, was the implicit discovery that gravitational waves were being emitted by this pair of neutron stars. Well, they're very far apart, 60 Earth diameters apart, so it's going to take them 1 billion or so years in order for them to fall together. And so we won't see them collide or anything, but it just shows that there are two pulsars that can be in very close proximity to each other, less than the diameter of the sun, and that they are apparently emitting, or they are emitting gravitational waves, but no gravitational wave detector had been built yet in 1974, nor had one been built by the time that they earned the Nobel Prize. It just showed that gravitational waves were the best explanation for the change in the period of the orbit of these two binaries, these two pulsars. Okay, so with that in mind, people were saying, wow, this is really great. There must be lots more of these things. So what happens when these two things collide? So there was a huge number of studies of pulsars. It's an active area of research of neutron stars and pulsars. And this radio telescope, which is the Lovell Telescope at Jodrell Bank Observatory, which is in Cheshire in northwest England, it was in 1957 when they first built it. It was the largest steerable radio telescope in the world at 250 feet in diameter. Now, Arecibo is not steerable. This is an enormous thing that's is 76 meters in diameter. So it's almost the width of a football field, an American football field. Now, the Green Bank Observatory in West Virginia is a bigger steerable scope, as well as the Effelsberg scope in Germany. But this is a big one. So this is a huge telescope, and it's one of the pulsar workhorses in the world. It's discovered a number of binary pulsars, as well as discovering 100 pulsars on its own. And in September 2006, they were able to assist in showing a different double pulsar, not the Hulse-Taylor pulsar, but a different double pulsar was also emitting gravitational waves. So the action of discovery of pulsars is a major part of radio astronomy. So what's a double pulsar look like? So one of the first known double pulsars opens up like this. Well, the Hulse and Taylor binary, one's a pulsar and the other must be a neutron star, but we can't see it. But this is a double pulsar, and they orbit. These two double pulsars orbit, and this is a double pulsar. The other one would be a double neutron star with only one pulsar being seen. That's the Hulse-Taylor binary. But this is a double pulsar seen by that telescope. So these two pulsars orbit around each other. That was discovered by the Lovell Observatory, and orbit around each other in about 2.5 hours. One of the faster pulsars spins 45 times a second, and the other spins 22 times a second. And as they orbit each other, they found that they too would be emitting gravitational waves in terms of how they're falling together and getting closer and closer. Now, each of these stars, each of these neutron stars, have much larger masses than our sun, but and these are incredibly large things and very, very, very close together. So how might a double pulsar be formed? So let's look at this, how they might be formed. In the upper left-hand corner, we see a supermassive star exploding in a Type II supernova. It becomes a neutron star with pulsar activity. Its companion in a close binary is also a massive star, goes through its evolution, and then while it's about to die, it's dumping stuff onto the companion to spin up the other pulsar into a millisecond pulsar. Then it explodes, forming a neutron star, and which is also a pulsar. So the upper left-hand corner shows the evolution over, say, 10 or so million or 20 million years to get those stars from main sequence all the way through the red giant phase. And as the second red giant swells up to full explosion, it'll dump material through gravitation, because the gravitational balance point dumps things across to the other neutron star. Then they explode, and now you get a double pulsar. So the right-hand side image shows our current observation of a double pulsar, where we see the beams coming towards us as these two stars rotate on their axes. Their fields are not coincident with their rotation axis, so we occasionally see these flashes of light from them. And as they orbit each other, they slowly lose energy in gravitational waves until they get close enough to collide like we see in the lower left. Eventually, this double pulsar will get closer and closer and closer as they orbit closer together. They will eventually collide in a titanic collision. As we see in the lower left, they'll form either a hypermassive neutron star for just a fraction of a second, and then they will form a gamma ray burst, which is the light that you saw in these jet-like structures. So the end result of one of these things is either a supermassive or hypermassive neutron star, which will only live for a few seconds before collapsing down into a black hole. So this is what we would call a kilonova. And the lower left-hand image shows what a kilonova looks like, which is a much about 1,000 times more energy than a standard supernova. That's why it's called a kilonova. And these things are also the sources for gamma ray bursts. So we can expect that some gamma ray bursts that we talked about in the previous lecture on gamma rays should be due to colliding neutron stars. And on August 17th of 2017, a gamma ray burst was detected by both the Fermi and Integral gamma ray observatories in orbit, and just a few seconds prior to their detection, the LIGO-Virgo Association, now the Virgo Gravitational Wave Observatory, was online in Europe. So now they have 3 observatories, unlike the others. The first initial discovery, which is simply by LIGO Hanford in Washington and Louisiana. This is 3 observatories able to confirm at the same time. And notice the gamma ray bursts occurred just a few seconds, less than 2 seconds after the arrival of the last moments of the gravitational waves. So this was the first ever joint observation of a gravitational wave and some form of light So the Fermi Space Telescope and the Integral Space Telescope both have triggering mechanisms that send information to observatories and observers around the world to go try to figure out what's going on and observe these things in, say, X-ray, optical, infrared, radio, what have you, as fast as you can, if you can. So they send out to massive observatories. Now the Virgo team had a glitch in Hanford that caused them to be delayed by 27 minutes after their initial detection, but they were able to clean up and say, oh, the glitch made it difficult to find, but they actually looked at it and said there's a signal inside there, and it was a massive, massive, massive signal that they were able to find, and this began the process of a worldwide effort to observe this event somewhere in the electromagnetic spectrum. This was the thing that was being hunted for. The light or electromagnetic counterpart to a gravitational wave event. So this is one of the landmark days in all of astronomy history. It was August 17th, 2017. And that signal looked a lot like this. And so what we see is the gravitational wave signal according to frequency, and so we have all this static, but then there's a signal that goes through the frequencies as a function of time left to right, and the actual event is at time 0 that you see there, but stringing all the way back, this looks like it started about 2 minutes prior when the signal actually could be detected. However, the triggering only happened about 30 seconds prior to it, and the summation of that trigger went out to everyone in the world 27 minutes later because there was a slight glitch at one of the observatories. What's funny is that they compare this signal and say, what is the chance that all this random static that you see in there could actually have just kind of organized itself or randomly positioned itself to make this shape? And they make enormous numbers of statistical studies to determine whether or not this thing is actually is a false positive, meaning that's just static, or whether or not it's a real signal. And so they create a false alarm rate characteristic, and they said that this was the only chance is that 1 in a trillion was the capacity for it to be a false detection. So they didn't think that for 1 in a trillion, that's over time, and that means that they would say this would only happen once in 80,000 years of observing. If they observed with the observatory for 80,000 years, only once would this happen randomly. So they said, well, this is a real signal, and they then scanned their data. They found the signal lasted 30 seconds. All of the other gravitational wave events that were occurred last only fractions of a second. So this was incredibly different than all the other signals combined, and because it lasted a lot longer, that means it was much less massive. Because more massive things, they change more quickly as they're about to collide. So they were much less massive. The only thing I could think is that they caught their first gravitational wave from neutron stars, since all the other things were more massive and much more quick. Just like the first one I showed you, it's a quarter of a second from rising out of the noise into the final chirp at the end. Note the frequency shows low frequency at the bottom and high frequency at the top, so literally all this would sound like is whoop. That's what it sounds like. It's like a whoop. And this was a merging neutron star because of how long it took and basically the signal itself. All right. So how do they actually know where to go and look for it? So then the race was on to find this thing. So the Fermi Space Telescope could see it in an oval, Integral could see in a band, and then LIGO and the two LIGO observatories and the Virgo observatory could see in a banana-type shape and shrunk it down. And so all those circles that we saw before, those are the possibilities of where it could have been in the sky. So you saw that there's a very small number of objects that it could have been. And they were able to isolate the location in the sky because the Virgo detector in Europe didn't detect anything. Remember, the observatories from the previous lecture showed that you had to actually get a signal by having the gravitational waves pass perpendicular through the detector. The fact that it didn't get a signal at all in Virgo meant that the gravitational wave signal did not go at any angle perpendicular. It went flat to the observatory rather than perpendicular at any level. So since it went flat, they were able to reduce the entire field of view to about 30 square degrees, or about 60 times the size of the full moon. And that launched a search, a massive search, and within 12 hours, this galaxy had been seen to have some sort of event happening in it. And this galaxy is NGC 4993. And NGC 4993 is an elliptical galaxy about 130 million light years away. And on the left-hand side is a Hubble Space Telescope image from April 28 of 2017, and on the right is from the SWOPE Supernova Survey from Santa Cruz, where there's a new bright dot right in there. And this was taken by that observatory at that date within 6 hours of it. And when they saw it, they said, there it is. This was the first optical image of this observatory, of a gravitational wave event. Now, that's not gravitational waves we're seeing. We're seeing optical light, visible light that came from something that captured gravitational waves. One of only a handful of galaxies inside the search area for this object. So the SWOPE team was able to compare against other previous Hubble Space Telescope images, and that's when they knew they got it. So what's funny is that apparently the people at Santa Cruz, when they said, it didn't really elicit this huge reaction. Hey, there's something new. It's like, oh, there's a dot there that wasn't there before. Interesting. Because they're hunting for supernovas, and a kilonova is just like that. It's just another little bright dot right next to the galaxy. So what happened was, this was the first detection in visible light, but with optical light of an object like this. And this is bright enough that if you had a half-meter class telescope or a 1-meter class telescope, you would easily image this galaxy. In fact, they started about the 20th or so. And it's per pay amateur class observatory, but they also can use for research. The larger instruments then could easily have observed this event. So the first light with Hubble Space Telescope, Hubble swung around, and they swung the Hubble Space Telescope around to take a look, and yes, they saw it fading away. Other observatories had seen it within 12 hours. Hubble Space Telescope watched the flare die over the course of 6 days. They started dying on the 20th or so, 22nd or so, and started watching it over the course of 6 days. Other things to do, and they couldn't exactly rip it away. But they got the Hubble Space Telescope as soon as they could to see this kilonova event and watch the fading glow of this object. It was also observed in infrared. This is the Spitzer Space Telescope, run by NASA JPL Caltech. And the Spitzer Space Telescope also saw the event. They were able to, they were looking specifically in the channels of 3.6 and 4.5 microns, which is much longer than visible light. It's deep in the red, and so they were able to see it in infrared. Also, the Chandra X-ray Observatory, the circles show where it is. In the previous, on the night, there was they were also in the previous section, the gravitational wave event itself only showed up later, and so there was a counterpart that occurred a little bit later, not immediately, in X-rays. And furthermore, the very large array in New Mexico, the VLA was swung over there by Greg Hallinan and Kunal Mooney. They got their, the little arrow points out the object. The center is the supermassive black hole, the center of that galaxy. But this is the VLA radio image, and that radio image comes from the interaction of the material in the surrounding medium around it. So this is also part of their work. And so when they were this is part of a high-speed alert that they actually working with too. And the Australia Telescope Compact Array, or ATCA, also detected it on September 5. So VLA and radio observations occurred too. And here we can see a little summary plot of it with a Hubble Space Telescope image. We can see the Swift Ultraviolet Observatory taking ultraviolet pictures of it. Gemini South is, instead of Spitzer now, looking in the infrared, and the VLA on the right. So this was observed by many, many, many groups. So what did this look like if you happen to have been close up? A merging pair of neutron stars. First, it would take about, their merge took about 2 minutes, but the last merge of it took fractions of a second. And there it was, they merged together, and as they exploded, they emitted the gravitational waves, and a huge burst of gamma rays came out, and material flowed out from them in the cosmos. The gamma ray bursted material then intersected with the interstellar medium to form the gamma ray burst that we've seen in other objects. This particular thing was, as they plowed through together, the amount of material that was turned into mass was about less than a quarter of a solar mass. And so we see that when neutron stars make the collisions, we're just summarizing it here. The upper right-hand corner shows the collision of the two neutron stars, and as they collide, they form gravitational waves, which are kind of the shimmering ghost rings that you see coming out. Those are the gravitational waves. They come directly from the interaction, the collision of them. So it probes general relativity in the very, very, very strong region of where things are going crazy in gravity. But then the light comes later, in a couple seconds later, as those jets are formed, and then we see the jet in the upper right and the lower right, and that as the material slams into the interstellar medium around it, that shock of the material heats the material such that it glows in gamma rays. And that's the source of the gamma ray light. And we talked about that in gamma ray bursts, in the gamma ray burst lecture, as we see in the upper left-hand image that comes from that lecture. But most interestingly is the lower right image. It's all the debris that came out from this collision. Because it probably formed a black hole, but not all of it went into the black hole. The total amount of material that went into becoming the black hole was kind of minimal. So the merging of it converted about a quarter of a solar mass into gravitational waves, and but the important thing is that material that came out that didn't fall into the black hole created huge amounts of heavy atomic nuclei. In fact, it was estimated and then subsequently seen in the spectrum of this kilonova, because so many telescopes and observatories could actually take a spectrum of this cloud, of this light, from a distance of only 130 million light years, that it was determined that approximately 16,000 times the mass of the Earth in heavy elements was formed, which is wild. And approximately 10 Earth masses of gold and platinum were formed at that time. So just think like 10 Earths of gold and platinum were made in that moment of collision. So this is very interesting because this has been shown in terms of the follow-up by the Chandra X-ray Observatory, because heavy elements like these, when you get X-rays, or at least the products that would radioactively decay to them in X-rays, because they're coming off in that explosion, that kilonova event, strongly excites the nuclei, as well as creates radioactive elements that would then decay to these heavy nuclei, such as gold and platinum. So there's a lot of X-rays that come in the spectrum, and X-rays determines what the material is. So that's how we know that that there was a huge amount of gold and platinum that was made there. In fact, this provides direct observational support for an incredibly important element of the Big Bang. The Big Bang produced the hydrogen and helium of the cosmos. Stars such as the massive stars like Betelgeuse and Arcturus, supermassive Type 1 supernovae, such that would have formed the pulsars in the first place, those would give us like oxygen and aluminum and phosphorus and argon and iron and nickel and cobalt and all other things like that, up to krypton or so. But those things would create and push out the iron. But the very heaviest elements were not, the mechanism that was understood to be creating them would not have been an exploding white dwarf, would not have been an exploding supermassive star, wouldn't even be, it would have to be the destruction of neutron stars. So if you have two neutron stars merging, they seem to be creating most of the heavy elements, and that's the color yellow in this particular periodic table set that we're looking at. They would be creating most of the heavy elements, including all of the iodine, all of the platinum, and nearly all of the gold in the entire universe. So all of the gold that you've ever encountered was created inside of as a result of two colliding neutron stars, and this is observational evidence for that. This is the first observational evidence for it. It was theorized up until this point, but now we know that it's actually occurring. That's just an amazing, amazing thing, and that was discovered by the event that happened on August 17th of 2017, the first observation of two neutron stars colliding, both in gravitational waves as well as in the electromagnetic spectrum all across the spectrum. One of the most studied transient phenomena in the history of astronomy happened in that day. Well, what this means is that there's a lot more to see of all of the gravitational wave events. And so here's a slide that shows the ones that have been seen. You can see there's 5 events that have been seen by the LIGO-Virgo collaboration, and there's 5 black hole mergers where the 2 black holes collide. Now they don't make heavy elements. Why? Because black holes are already inside their event horizon, so nothing gets out. So the black holes simply collide. They don't make a hypernova type explosion. They don't make a kilonova type explosion. They just make a gravitational wave event. However, neutron stars make a lot of light because their actual physical structures are still objects of extreme density, so they rip them apart and will create a huge amount of debris and a gamma ray burst. So now that we know that gamma ray bursts come from 2 neutron stars colliding. We do know that. We also know they come from hypermassive stars collapsing. But this was the most studied, as we can see, of all the neutron stars that have been seen by LIGO-Virgo. The LIGO-Virgo combination actually showed the first one ever. And hopefully there will be many more to come as they're taking the system offline to do some upgrades, because it's a huge undertaking actually to do this. So only 6 have been found so far as of the fall of 2018, and hopefully there will be more in the future, because this is the future of astronomy, is gravitational wave observing, which involves enormous collaborations, extraordinary commitment, and then commitment between particle physicists, engineers on the ground, and astronomers looking at multiple different kinds of telescopes. Well, this incredible thing to summarize that in a little fact sheet. Okay, zip through it because this is really neat. All sorts of stuff, there's some anecdotal things, and finally, there's some websites for you to go take a look at, because, heck, that's what they're all about. The LIGO Observatory, as well as the Virgo Observatory, and this is one of the most important things that happened in 21st century physics. Thanks again. See you soon.
which is entangled with another thing, develops properties which are very different than what Einstein said black holes are like. Now remember, one way of entangling the black hole with something else is just to let it evaporate for a while. Black holes evaporate, Hawking radiation. As they evaporate, incidentally, this is something that any system will do. It will eventually evaporate. It could be a puddle of water. A puddle of water, H2O, will also evaporate. Let's suppose it's completely isolated in outer space, a little puddle of water, and little droplets will go off. The little droplets will be entangled with the puddle. As the puddle shrinks, it will become entangled with the outgoing products of evaporation. Eventually, when there's enough evaporation product out there, the bubble here will be highly entangled with what's out there. So the way that AMPS imagined it, they imagined this object over here was really just Hawking radiation coming out. Now you could take that Hawking radiation and collapse it into a black hole, it would still be entangled with it. Yeah, it would just actually be entangled with the outgoing radiation, and different parts in here would not be entangled the way you might have expected. It would just be true. But there's no such thing as a horizon, and there's no reason to think that there ought to be a smooth horizon. So it only comes up as a crisis when you think about black holes. Again, it could simply mean that the black hole doesn't have an interior. Nobody wanted to believe that. I think very few people do believe that the black hole doesn't have an interior. And it certainly violates the principle of equivalence, of Einstein. And so the question is there no other way out? Is there no way that this somehow could be misleading? Well, there's one way out. As I said, these are logical qubits. These are logical bits of information. And a logical bit of information over here, which is the thing we call A, which is supposed to be entangled with a logical bit of information over here, despite the fact that the logical bit of information over here is entangled with something else that's given another name, B prime. B and B prime are entangled. We built the thing that way. B is supposed to be entangled with A, but there's something wrong. There's one way out, and that's that A and B prime are the same thing. A and B prime really are the same thing. Is that possible? Is that completely nuts? AMPS said that's too crazy. They're too far away. This object could be off an Alpha Centauri, this black hole, let's say on Earth, and the thing which is right behind the horizon over here is clearly near Earth. It's not near Alpha Centauri. So it doesn't really make sense to say that A is really the same object that's out here. But they also had an experiment that they imagined. Here's the idea. The idea is that a bit of information just behind the horizon is really the same bit of information as over here. Okay, so here when various people said this and said maybe this is what's going on, the answer of AMPS was very, very clear. They said, no, that's complete nonsense. And here's the way to prove that it's nonsense. Supposing A really was the same as B prime, and B prime was off on Alpha Centauri. Well, Alice, who was at this end, could make a disturbance of B prime. She could measure something in B prime. Measuring things disturbs them. So by Alice manipulating the B prime, which is in this black hole someplace, which is entangled with B, by measuring it, first of all, she has found out something about B, but by assumption, she has effectively measured something just behind the horizon of the black hole. Well, that's crazy, because by making a measurement of something, you disturb it, and the result would be a disturbance just behind the horizon of the black hole. Amps said, and the disturbance means some energy deposited there. Some energy deposited there by the measurement. Anytime you measure something, you tend to change its energy. But by measuring what was out here, you made a disturbance over here. Well, how crazy. One of them is off on Alpha Centauri, the other is over here. That can't be right. Or, you could say one of two things. By measuring what's out here, perhaps you did create a particle behind here, but that's a little bit crazy. It's too far away. So if there was a particle behind there as a consequence of Alice doing something over here, that particle must have been there whether or not Alice made her disturbance. She's just too far away for it to matter. And so the conclusion was that there must be loads of particles behind here, one for each possible measurement that Alice could possibly do on this thing. That's what was called a firewall, and that was the basic paradox. That was the unhappy paradox that Amps concocted. There was one assumption here, and it seems so obvious that, that it was obvious. Namely, that there's no causal connection between this black hole or the environment of this black hole. I draw a little bubble over here to indicate the thing connected with this black hole. That there's no causal connection between the bits of this black hole and the things which are behind the horizon over here. In other words, there's no causal connection means a way of disturbing things over here that will show up over here. And that seemed obvious to everybody, except it seems that it's wrong. It seems that it's wrong, and to understand why it's wrong, we need to think about the other half of the EPR connection. This was all about entanglement in the context of black holes and a puzzle about entanglement. The other paper from 1935 had nothing to do with quantum mechanics. It had to do with the geometry of the interiors of black holes. ER invented something called an Einstein-Rosen bridge. I don't think they called it an Einstein-Rosen bridge. It was called Einstein-Rosen bridge afterwards. And what they did was they looked at the mathematical solution of Einstein's equations that I don't know how they managed to look at the Kruskal solution before Kruskal was born. I'm not sure, but somehow they did. And they knew enough about general relativity. Einstein was pretty good at general relativity. But for those who know what a Kruskal black hole is, it's basically a black hole. I'm going to draw the Penrose diagram of it. Now here we're coming to things that I'm going to assume you know a little bit about, but I'll explain a little bit as we go along. That's a space-time picture, time going up as usual, space going horizontal. It's a space-time map of a black hole. Let me explain it to you. On these kind of diagrams, light moves at 45 degrees. Light moves at 45 degrees in the outward arena. If you're out here, this is spatial infinity. When I say it's a map of space and time, which is distorted in places. It's distorted in the same way that a Mercator projection of the Earth is distorted. It's squeezed around in such a way as to be able to put all the space-time on a black hole. So this is very far away over here, off at infinity. This is time infinity. Clocks go to infinity up here. Here's the horizon of a black hole, and here's the exterior of a black hole. The only thing you should notice is if some poor person happens to fall through this line here, they are trapped. This is the singularity of the black hole, and it's a bad place. It's a place where you won't survive. This is the horizon of the black hole. If you fall through there from the exterior region, you're dead. You're doomed. Anyway, you may not be dead, but you're doomed. You don't hit that singularity. Now, this is the exterior of the black hole, but strangely, the black hole seems to have two exteriors. One on this side and one on this side. And you can fall through from this side or that side. Well, it's really two black holes. It's a black hole on this side, and it's a black hole on this side. They're, in a certain sense, infinitely far away from each other. You can't go around from one side to the other. You'll never get there. Here's a picture of what this crystal extension, and in what sense it's two black holes. It really represents two disconnected regions of space, completely disconnected. Here's a region of space, or a space. That stands for space. Not space-time, but space. X. That's the right side. The left side, another region of space. And connecting them, you can go from one to the other by passing through something that John Wheeler called a wormhole. When you walk from here to here, right through that point, you walk through the horizon of one, and you show up just outside the horizon of the other. That's over here. There's the horizon. So, falling in, well, crossing over, not falling in, but crossing over from here to here, is crossing from here to here. Einstein and Rosen drew this picture. Somebody called it an Einstein-Rosen bridge, and it stood for this diagram over here. It's two completely disconnected worlds that are only connected by virtue of this wormhole. It's a real solution of Einstein's equations. It exists. It exists mathematically. It has some properties. First of all, the region over here, as you cross from here to here, is pure empty space. Nothing strange going on there. If you were able to pass from here to here, you would find nothing strange there. It's just empty space. That implies that there is entanglement between this side and this side. Entanglement across here. Another way to... Yeah, if you actually wanted to walk across there, yes, you would. But, but we're not really walking across there. We're just talking about the properties of space from one side to the next. I don't really imagine walking across there. I imagine a series of observers over there making measurements, and then they could correlate their measurements by sending signals into the interior here. So they could ask somebody on this side and somebody on this side making measurements whether this side and this side are entangled. They're supposed to be entangled if space is really just flat over here. Space is just empty over here. And that says that in this picture of what's going on at an instant, there must be entanglement between one branch and the other branch. In other words, to put it another way, this represents two entangled black holes, one over here and one over here. Now, they're on two completely disconnected spaces. You can't go around the outside, forget going through the interior. Can you ever go from here around to here? No, because they're just disconnected. They're not a connected space. But you can do the same thing in another way, or very closely related. Imagine a very big space. but I'm going to draw it in a funny way. Here's space, big. I'm just going to fold it like this. Now that's not really done anything to it. It hasn't changed the geometry, the geometrical relations. It's just a way of exhibiting it. If I had space very big and I might want to pull it all into this room, I don't know, a big sheet of cardboard, big, huge sheet of cardboard, I might want to bend it over like that to get it into the room. It doesn't change any of the relationships on the cardboard. So we do that. Take a big region of space and we bend it over. Let's see if I can do this. You can see the picture. I haven't really done anything to it. I've just exhibited it in a way that gets it all in a small region. And then we take one of these Einstein-Rosen bridges and put it between here and here. These are, as far as the external world goes, these are two black holes very far from each other. You might have to go a zillion light years to go from here to here around the outside. But strangely, it has the property that you cannot go through the Einstein-Rosen. This is one property of Einstein-Rosen bridges that is important. You can't actually pass through them. You can see that. Where's our diagram? Here's our diagram. Can you get from this side to this side? Can you get from here to here at all? No point on this side over here can send a light signal that will ever get to this side. No point can send a signal that will get to the other side. But what can happen is they can meet at the center. So the meaning of that is, although you cannot send a signal through the Einstein-Rosen bridge, somebody could jump in from the side and jump in from the side and meet at the center. Same thing here. If somehow this kind of thing could be manufactured, then these two places could be, as far as the external world goes, it could be 10 billion light years or more around there. Light years. And yet, if Alice jumps into her black hole and Bob jumps into his black hole, they have a chance of meeting at the center. That's a very crazy thing, but it's a consequence of Einstein's equations. What do you need to do to make two black holes that have this kind of connectivity? The answer is they've got to be entangled. If they're entangled, then they will have exactly this kind of connectivity. So if you can make black holes which are entangled, and you can make them by taking entangled collections of particles and collapsing them into black holes. They have the astonishing property that in principle, no matter how far apart you take them, you can do things to them and then jump into them and meet at the center, and not in a terribly long time, but almost immediately. This was always considered a kind of science fiction-y thing. But it is an actual property of Einstein's equations together with the ideas of entanglement. If you could make two entangled black holes, they will have this property. Okay, so now we can come back to this crazy entanglement story. Let me draw one more way. Let me draw one more way of thinking about these entangled black holes, which are very far from each other. Let's not fold over space in that way. Let's just take flat space. Here it is, big. Put a black hole over here. Here's the inside of the black hole. Here's the horizon. Here's the inside of the second black hole. There's the horizon. What we're talking about is a geometry. What the Einstein-Rosen bridge is it's a geometry that if you fall into here, you come out over here. You draw this. Well, you can see. If you fall into one, you appear in the interior of the other black hole. This point and this point are not really far apart. They're both inside, but Alice and Bob can jump in and discover, right. The one thing you can't do is use this to send information from outside this black hole to outside this black hole. That will not work. But you can use it to send information from outside this black hole to the inside of this black hole. The only way Bob on this side would ever know about it is if he was willing to jump into the black hole. This kind of connectivity, first of all, is the real properties of solutions of Einstein's equations. It appears that it is closely connected with whether the black holes are entangled, and it basically resolves this puzzle. It basically resolves this puzzle by mucking around with things over here and doing disturbances. In fact, what will Alice do? She makes a disturbance over here trying to measure something. Odds are she will disturb something and send something into her black hole over here. If the two black holes are entangled, the disturbance will appear right on the other side here.
So that's the solution to the paradox you mentioned?
That's the solution. That is... when I say it's the solution to the paradox, I do not mean to say that everybody accepts it. It means to say that this is a... Yeah. Now,
Paradox gets resolved, and then you just start.
not if B and B prime are the same. If B prime is the same. So if they're close, then they can influence each other easily.
No, so carrying it out to this word, does it mean that therefore, if you jump in on A, you come out of B?
If you jump into A, you will not come out of B. You see that? You come back to here. If you jump in from this side, you will not get to the outside of the other one. All you'll do is get into this side, into the black hole on this side. On the other hand, if Alice also jumps in, Bob, I don't remember which one is Alice and Bob, they can meet at the center. Okay. Not unless you're willing to jump in. Right.
The point is, you can never know if this is true, because assuming we're outside the black hole by definition, so it's an irrelevant experiment, or a full experiment in some ways. We can never know. The information can't be verified. You can never resolve the entanglement. So the information can flow out.
Unless you're willing to jump in.
But then you're inside, and then...
Yeah. Nobody's going to do this experiment. We're trying to unravel an inconsistency. We're trying to unravel an inconsistency between two principles. And what we're finding is there's no inconsistency. But what you have to accept is that there can be this kind of connectivity, spatial connectivity, surprising, unexpected spatial connectivity as a consequence of quantum entanglement.
Is a non-zero amount of space-time required for entanglement to be present?
I think what this is saying is that in a certain sense, entanglement builds space-time. Anytime you have entanglement, a bit of this kind of thing happens. It builds a kind of space-time between the two things. Now, if they're just electrons and they're entangled, nobody's going to jump into an electron. You can't get Alice and Bob to jump into different electrons at different places. The only content of the entanglement is the usual content of entanglement. What this is saying is somehow when entanglement gets big enough between big enough macroscopic objects, when it becomes big and entanglement between big macroscopic objects and those macroscopic objects are made very, very dense, that entanglement turns into space-time, turns into new regions of space-time that were not there if the systems were not entangled. No. Now, I think this is not too contentious. I think most of theoretical physicists who are working on these things more or less believe this.
You're saying essentially that entanglement is more fundamental. So entanglement creates space-time. But
I don't know that I
there
want to say which
there
one.
can exist things in space-time that are not entangled.
There can exist things in space-time which are not entangled, and there will be no spatial connectivity of that type. You can have two black holes which are not entangled. Absolutely, you can have things which are not entangled. Two black holes which are not entangled will not have this peculiar feature of a connectivity between them like this. Bob will jump into this one, Alice will jump into this one, and there is no chance at all that they will meet at the center if they're unentangled.
This diagram, doesn't that assume that the black hole existed from the beginning of time minus infinity?
Ah, good point, good point, good point. Yeah. This diagram, yes. But you can imagine that the upper half of this diagram, let's take the upper half of this diagram, well, in this fashion, that the upper half of this diagram represents the following process. You started over here, in a sort of neutral position, neither on the left or the right, and you started creating entangled pairs. Lots of entangled pairs. Electrons and positrons, if you like, any way of making entangled pairs of particles, and that's easy. And then you take half of each pair and bring them over to here, and half of them over here. And remember that these are entangled with these. Let's represent the fact that they're entangled by drawing lines between them. This is simply a notational device to say this particle is entangled with that one, this one is entangled with that one, and so forth and so on. No content to this other than whatever content is supposed to be associated with this entanglement. Then having done that, we now collapse them into a black hole. We make enough of them so that either their own gravitational field will cause them to gravitate to form a black hole, or we compress them. We put them between the jaws of a vice and we squeeze them down until they form a black hole. And lo and behold, these vertical lines here effectively coalesce into something when there's enough of them that they form a new region of space. Emergence of a new region of space out of quantum entanglement. That's what these things are saying. And we're learning that enough entanglement at a small enough volume will manifest itself as a new region of space that now has the possibility not of communicating from the outside to the outside. Entanglement never allows that, but communicating between the outside of one and the inside of the other. Yeah. Yes, it will have an Einstein-Rosen bridge of about 1 Planck area. Yes, that's a good question. You have two, that's a very good question. You start with two black holes which are unentangled, and you take the... Entanglement is not a thing which is either yes or no. There's a magnitude of entanglement. The magnitude is called the entanglement entropy, but it's basically a measure of how many entangled pairs are shared between the two sides. If you took one entangled pair and dropped it into here and into here, then yes, you would make a very, very primitive Einstein-Rosen bridge, for which there is no particular meaning other than the fact that they're entangled, but you could draw it by saying there's a very simple, primitive, Planck scale, tiny, tiny microscopic bridge between them. And, but I assure you, nobody is going to jump into there and meet at the center. So you can ask, how many do you have can ask, how many do you actually have to assemble before you can make something big enough that people could meet at the center? And the answer is this, that the number of entangled pairs manifests itself in the area, the minimal area of the bridge. So if you want to make a thing with an area that's big enough for you to fit into, you have to have started with enough entangled pairs that, that you'll make a big enough area. Something like, let's see, I think 10 to the 76th of them, 10 to the 72 of them, in order for you to fit in through the bridge. So that's right, exactly. So it's not easily done. Not particularly. But probably in practice, yes. It only has an appreciable effect on large-scale space-time if the entanglement is strong. Only when you collect enough entanglement like this and collapse it do you make anything resembling ordinary space-time. But yes, I would say yes. That would the idea that time goes to zero at the horizon is just a statement that that's a point over there. It does play a role, but the main role that it plays is saying that you can't escape outside. You can't escape from the inside to the outside. Or better yet, you can't pass from the exterior of one to the exterior of the other. All right, so the lesson to learn here is that the connectivity of space can be more interesting and more involved, topologically interesting as a consequence of entanglement, and that does resolve the ants paradox. Whether ants themselves would agree, I know the answer to that. They agree when I'm around. That's all I know for sure. Oh, no, this is kind of a slice in pepper. Now you can ask what happens. All right, good. There's an interesting issue here of what happens as time evolves. This is the slice right through the middle here, which you can sort of think of as what happens when you first collapse the particles into the black hole. When you first take them, first they're particles, and then you collapse them, and you make this thing that's just straight through here. So let's look at it. Starting here, I'm not literally walking, I'm just moving my finger from one side to the other. And going from here to here, what you're doing is going from out here through here, that's this point over here, and then going through and coming back out. But you can't do that without exceeding the speed of light. Okay? Nevertheless, there's an imaginary excursion walking across there, that's this. So this picture is what happens at t equals 0 when the horizons are just touching. Okay. What happens later? What happens as time goes on? We're going to talk about this next time in greater detail, but as time goes on, the interesting part of the Einstein-Rosen bridge is the part behind the horizon. Once you fall through here, you're stuck in the interior of the black hole. You can't get out. You're going to hit the singularity. So this is the extended horizon over here. This is the extended horizon on the other side. And the interior of the Einstein-Rosen bridge, or the interior of this object, is what's in here. Now, notice an interesting property. As time goes forward, let's just draw time going forward like that, the Einstein-Rosen bridge grows. It started with the horizons touching each other. It started. Let's draw it this way. Right over here, the horizons are touching. That's what happens as you move in, you get to this point over here, that's right over here, and then you go out the other end. Okay. At that point, at time t equals 0, the Einstein-Rosen bridge is as short as it can be. As time goes forward, the horizons start to separate. The two horizons of the two black holes start to separate and leave between them a region of space. So what does that look like? That looks like this thing starts to grow. It starts to stretch. It doesn't shrink, but it starts to stretch. If you work out Einstein's equations, you will discover that the solution grows and grows and grows. And in fact, in going from up here to across here, it's infinitely far, way up in these corners here, way up in these corners. So as time goes forward, this Einstein-Rosen bridge grows. Its growth is one of the reasons that you'll have such a hard time sending the signal completely through the Einstein-Rosen bridge. You can't, and it's because as you're trying to send the signal through, it's growing. And it's growing fast. It grows basically with the speed of light. So the Einstein-Rosen bridge grows with time. It's a very interesting question. What properties of the quantum mechanics are encoding this growth of the Einstein-Rosen bridge? This is the problem. The resolution of the original AMPS paradox is essentially that there is a causal route, it's through the wormhole if you like, a causal route from the edge of this black hole over here to the interior of this black hole. It's sort of into this one and out over here. There's no problem left once you buy into that. Okay? But there's still something interesting to understand. What is it about entanglement? What is it about quantum mechanics? What is it about the nature of these systems that encodes the fact that the Einstein-Rosen bridge grows with time? It grows, it doesn't shrink. And how long does it grow? Classically, according to classical general relativity, it grows and it grows and it grows forever, getting longer and longer, with its length being proportional to the time. That's a puzzle. That's another puzzle. It's a new puzzle. And the reason it's a new puzzle goes something like this. Black holes are thermal objects. They're objects with a temperature, with an entropy, and they're in thermal equilibrium. Well, they don't start in thermal equilibrium. When they're created, they're out of thermal equilibrium. But thought of as quantum mechanical systems, they're systems which are thrown together and very quickly come to thermal equilibrium. The time that it would take a solar mass black hole to come to thermal equilibrium is basically about a millisecond. A big solar mass black hole, a couple of kilometers big, when it collapses, it's way out of equilibrium. Why? Because the sudden collapse is a sudden process. Way out of equilibrium, thermal equilibrium, and then the internal dynamics of whatever it is that's making up the black hole equilibrates, and it takes about a millisecond for a solar mass black hole to come to thermal equilibrium. Very, very fast. And then what happens to it. Let's assume nobody is poking around at it. But you're watching it from the outside, and you're describing it by quantum mechanics, you're describing it by a combination of quantum mechanics and whatever else describes it. What do you find happens after that millisecond to the black hole? The answer is nothing. Once things come to thermal equilibrium, nothing happens. That's it. That's about all that ever happens. Once you come to thermal equilibrium, the evolution of systems just ceases. Unless you disturb them again. Unless you disturb them. Unless you do some disturbance to them. It's also possible for accidental fluctuations to take place. So let me put a thermal equilibrium. My favorite example is the air in the room. Let's take all the people out of the room so that we don't disturb the system, and start with some very strange configuration of the air. The usual configuration people like to talk about is all the air in the corner of the room. That's way out of equilibrium. That's like the black hole just being allowed to collapse suddenly. And then what happens? The air eventually fills up the room uniformly, and then nothing happens after that. All sorts of interesting things happen in between, but nothing interesting happens after that. The air just fills the room. So thermal equilibrium is usually thought of as the end of interesting things happening. And it happens fast. It happens fast. In this room, it would probably take a couple of days for the air to really equilibrate. But in a black hole, because of the compactness of it and how strongly the different pieces of it interact with each other, it happens very fast. So after a very short amount of time, somebody looking at this black hole will discover that it's simply stellar. It was created by a process like this, like process of collapse. They'll discover nothing happens afterwards to the black hole, looking at it from the outside. If that's the case, that nothing interesting happens after thermal equilibrium, then how do we account for the fact that the interior of the black hole grows and grows and grows forever? What's going on that simultaneously allows us to say that from the outside of the black hole, it thermally equilibrates and nothing flat, and yet that same quantum mechanical system, something is going on that says that it is evolving and evolving and evolving, the interior geometry evolving essentially forever and growing. How do we understand that? That's another form, that's another paradox that I think we'll take up next time, and it's the paradox of complexity, of quantum complexity. Now, as I said, I'm telling you what I think. The purpose of these lectures is for us to lay out what we're thinking about here. What you will find, of course, is that ongoing research, as it happens, generally does not involve consensus. So this is not a thing which has reached the stage of consensus, but this is what I think. This is going to go into a historical record. This historical record will be a record of the research that's performed at SIPT by the various people who do it. And 100 years from now, historians will come and they will look at it. And what will they say about this? We'll find out. Hopefully, this record will be of some interest to people. It'll be public. It'll be available. And hopefully it will be interesting. Anyway, let's see. Should we go on a little bit or not? Yeah, let me tell you a little more. A little bit more. How do you make entangled black holes? Well, I told you one way to make entangled black holes is to take a bunch of entangled particles and then collapse them. But it's by no means obvious that makes a black hole with a wormhole, two black holes with wormholes between them. That's a sort of guess. But there is a mathematical or physics-oriented process that when you actually solve the equations, you do discover that you made two black holes with a wormhole between them. And this is old process, I told you about it. By a process, I don't mean, could you do this in the laboratory? In principle, yes. In principle, yes, this could be done in the laboratory. It would be very hard, it would take a long, long time, and involves very, very difficult conditions. But I'll tell you what the process is. You start with a very primitive and simple version of it. It was discovered by Julian Schwenger. Julian Schwenger was a great, one of the great discoverers of quantum electrodynamics. And it's called pair creation in an electric field. Pairs mean electron-positron in an electric field. You take an electric field, a big one, capacitor plates, plus, 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 minus, 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 minus. You put enough charge on them to make a very, very big electric field. Now, one of the problems with this is that you couldn't make such a big electric field in the laboratory. It would simply discharge itself. You know, you'd blow up your laboratory if you tried. So, but in principle, you make a very, very big, and it can also do it with a magnetic field. But you make an electric field of very, very sizable big value. And what will happen is the vacuum fluctuations, the creation, remember, there are constantly in the vacuum the creation of pairs of particles. In particular, electrons and positrons, virtual particles, a minus charge and a plus charge. Then they form and then they collapse, and they form and they collapse, and they're constantly an ongoing thing. So supposing over here, right in the middle, a plus charge, no, a minus charge, an electron and a positron were created. Left without the electric field, they would just recombine. And these processes take place continuously in empty space. But the electric field exerts a force on the plus charge this way, and the electric field exerts a force on the minus charge this way, and it simply pulls them apart. Out goes a plus charge, out goes a minus charge. Now, of course, if you really have a capacitor, then the plus charge will get absorbed into the capacitor. But imagine this is so big that these particles will fly a long way before we have to worry about the walls of the system. So we've created a pair of particles, a pair of plus and minus. In fact, we've created an entangled pair. This pair is entangled in several different ways, but in particular, the spins of the particles are entangled. So we've created a primitive entangled pair. Now, if you really make the electric field big enough, you can do something which can be calculated. It's possible to calculate from basic rules of quantum mechanics and field theory. You can calculate the pair creation of something much more exotic than an electron and a positron. You can calculate, literally calculate the process, and you can calculate the probability for it, and you can calculate how it behaves afterwards, of two black holes. A plus black hole, a minus black hole, and a plus black hole. These are charged black holes. Black holes can be electrically charged. Plus charge black hole and a minus charge black hole. This is just an extreme version of the same Schwinger process. Black holes, incidentally, have many quantum states. They're not like an electron, which has two quantum states, spin up and spin down. They have many, many quantum states. Many quantum states because they have a large entropy. Black holes have entropy, and so black holes have a lot of quantum states. Just little rearrangements of them. The black holes come out, and like the electrons, they come out maximally entangled. They come out in such a way that you could learn anything about this black hole. Remember, black holes are not just objects. They're objects with many, many states, many things going on in them, complicated systems. They come out maximally entangled, and the same way as the electrons, in such a way that in principle you can learn about anything in Bob's black hole from Alice's black hole. That's number one. So they're entangled. Number two, when you calculate the geometry, the solution of Einstein's equations that correspond to this, what you find is the solution has a wormhole between them. Exactly this behavior. Let's see, we can draw it on one of these folded pictures. Here's the folded picture. On the folded picture, on the folded strip, there's an electric field. The electric field could be pointing that way, a big electric field. And what happens is a pair is created. A pair of black holes are created, and the black holes are created with an Einstein-Rosen bridge between them. And then one of them is accelerated one way, and the other is accelerated. These are opposite directions, incidentally. This one this way and this one this way correspond to opposite acceleration, and this whole thing just slides off and eventually becomes two black holes very far from each other, which are entangled, and the Einstein-Rosen bridge moves with them. So that is a classic example. It's not classical, it's quantum mechanical, but it's a classic example of the pair creation of entangled black holes. You can then do this over and over again and collect yourself a large number of such pairs. So after a while, you have a whole bunch of ones going this way and a whole bunch of ones going this way. What would it look like? It would look like just a whole bunch of black holes connected by wormholes, connected by Einstein-Rosen bridges. The Einstein-Rosen bridges are hidden from our view because they're behind horizons. But then if you like, you can take them and you can collapse them into bigger black holes. And from following the structure of the Einstein equations, you discover that the bigger black holes are, number one, entangled, and number two, have Einstein-Rosen bridges between them. So this idea of entanglement being, if not identical to, at least a close relative of Einstein-Rosen bridges, this idea appears to have mathematical substance from a number of examples. We know other examples. And, we'll see. We'll see in 100 years whether it still stands. As I said, the next thing to try to understand, which is even stranger, in some ways even stranger, is what property of the quantum mechanical evolution of a pair of black holes corresponds to this growth of the Einstein-Rosen bridge. And we will talk about that next time. That's the subject of quantum complexity. Yeah.
By comparison, entangled, they have broken into just two particles that are entangled.
Yeah.
Einstein-Rosen bridge between them.
A very primitive one, which in some sense is no bigger than a Planck scale.
The particle is actually a black hole.
Yeah, but of course, a extremal black hole, it's an extremal black hole of 1 bit of entropy, the smallest possible. And even it's not really that either, but it's lighter than an extremal black hole. But yeah, it's related to the idea that there's no sharp separation between particles and black holes. Very definitely connected to that. Yeah. You know, if you look at the spectrum of elementary particles, you get light ones, heavier ones, heavier ones, heavier ones, and eventually you get up to an energy which is a mass which is large enough for them to have an appreciable gravitational field. At that point, they basically are black holes. So the sharp division into what we call black holes and what we call particles is not really a sharp division. It's a qualitative distinction. As I said, you can't jump into an electron. You can jump into a black hole, but there's a gradation of different sized black holes, particles being the smallest, and big ones being big. So that's a good point, that there's no sharp division between particles and black holes, and therefore there should be no sharp division between what we just call entanglement and what we call geometrical connectivity.
When did that concept first arise? So you have a geometrical solution that creates a wormhole or an Einstein-Rosen bridge that implies two entangled systems that are far apart. Is that part of this AMPS
Part of what?
paradox, or does that come long before the AMPS?
Well, I think it was really articulated clearly, most clearly after the AMPS paradox. But it was based on things that had been understood earlier, much earlier. There was a wonderful paper by a relativist by the name of Werner Israel in the early 70s who pointed out that this Schwarzschild-Kruskal version of a black hole here, the quantum state of it was a highly entangled state. Now, he didn't know what to do with it. He didn't have anything great to do with it, and it was more or less forgotten until Juan Maldacena, who is largely the hero of all of this to my mind, brought it up again in the context of modern string theory and modern ideas, and realized that these two disconnected black holes on two different sheets that the connectivity between them, the fact that you could send a signal through here, even though they were in some sense in completely non-interacting worlds, was a consequence of the entanglement. But in the context that we're talking about here, it dates to much more recent than that. It dates to a paper of Maldacena and myself. But it was, there was an evolutionary growth of these ideas. These ideas don't suddenly spontaneously appear from nowhere. The idea that it was a solution to the AMPS paradox, that was a paper by Maldacena and myself about a year and a half ago. But the growth of the idea of the connection, so let's see. There were a very important observation by a young physicist, not so young anymore. He used to be a young physicist. In fact, he used to be a postdoc here, Mark van Ramsdonk in Canada, who I think you could probably say it was his basic idea that entanglement is what holds space together. And that when space is held together, it's always entangled. And when it's entangled in the right kind of way, it means that things are juxtaposed in a smooth way. So Van Ramsdonk, and this is fairly recently. When was Van Ramsdonk's paper, Bartek? How long ago? Right, 5 years ago. And since then, people have been thinking about it. This Einstein-Rosen bridge picture is really a special case of it. It says that this geometric connectivity, if and only if there is entanglement. So either you have two disconnected black holes when they're unentangled, or they're kind of sewn together by the entanglement. That idea was really spelled out, not quite in this context, not exactly in this context, by Mark van Ramsdonk in a really great paper. There's really extremely interesting versions of it now being developed at Stanford, I'm glad to say, by Bartek and by Lampros here. And, so these are evolving ideas. They're all connected And what they're telling us is that the two subjects of quantum mechanics and gravity are not two subjects, that they're joined much, much more thoroughly and much more intricately than anything we imagined. We still haven't gotten to the punchline. We don't know what the punchline to all of this really is. We're seeing fragments of connections, and the connections are such that you get the feeling that someday there is not going to be quantum mechanics and gravity. I don't even think we'll call it quantum gravity. That has two words to it. It'll be gravity. Gravity. One word, some kind of system which just manifests different properties, and that you really can't think of gravity without quantum mechanics, and you can't think of quantum mechanics without gravity. We already see this here, that you can't think of the spatial connectivity of these two regions without thinking about entanglement, and you can't think about entanglement without thinking about spatial connectivity. This is an exceedingly, we are living in a golden age of both quantum mechanics and gravity. There are things happening that are out of the imagination that anybody had 15, 20 years ago, when quantum gravity was a complete mystery. It's not so much of a complete mystery anymore, but what is happening is, I don't know how to describe how exciting it is. It's incredibly exciting, and it's being pushed. It's being pushed by a very interesting collection of concepts from different areas. It's being very, very heavily pushed by what is called quantum information theory. Quantum information theory is basically about how information is stored and manipulated and used in quantum mechanical systems as a resource, how entanglement is used as a resource for communication, among other things. So the quantum information people, the quantum computer people, have developed a large number of concepts that are paying off in a totally different framework, in the framework of understanding quantum mechanics and gravity. And in fact, if I'm right about where this is going, in particular this paradox about what it is that accounts for the growth of these things, computer science is coming into it. Concepts from computer science, concepts like complexity. What is complexity? Complexity, I was down in Santa Barbara, and I joked at the beginning of my seminar, I was paraphrasing Douglas MacArthur. He said, old physicists never die. They just go to Santa Fe and talk about complexity. But, right. What is complexity in computer science? Complexity in computer science is a measure of how difficult it is to solve a problem. Solving a problem means two things. It means setting up a computer program to solve the problem and running the computer program. There are two ways that a problem can be very complex. One is if the computer program to solve it has to be very, very long. The size of the shortest computer program that can solve a problem is called algorithmic complexity. But then there's the question of once you've programmed the computer, how long does the computer have to run before it solves a problem? And that's called computational complexity. Computational complexity is something that's interesting for classical computers, but it's wildly more interesting for quantum computers. And that is now beginning to enter into the subject of black holes and quantum gravity, the complexity ideas. So the lesson from all of this is that there is some subject, and we're touching on it, and we're constantly touching on it in deeper and deeper ways, which is the synthesis of the ideas of space-time and gravity on the one hand, and quantum information theory, entanglement, complexity, and so forth on the other. And I would guess in 5 years we will know a lot more. When will we know everything? When will we have a complete theory? Bartek, when will we have a complete theory? You're not telling me. I hope you're going to make the complete theory while you're still at Stanford. Right. But it could be 100 years, it could be 50 years, it could be 10 years, it could be, who knows? We don't know. Next time I'll tell you a little bit about quantum complexity and its relationship to the growth of the Einstein-Rosen bridge. As I said, it's the growth which prevents signals from being able to go from one side to the other. And hopefully we do have another candidate to give another series of short lectures. It's Sean Hartnell, who will also talk about gravity and information. But he will be talking about, I believe, the connections between gravity and condensed matter physics, superconductivity, that sort of thing. Very interesting. So we're going to continue, and I'm going to lean on my colleagues till we have everybody telling you what it is that they're interested in. And we'll do it over and over and over again every time physics changes a little bit, every time they change their minds and say, well, it's wrong, let's do something else. We'll create a history of them. Anyway, I hope you're enjoying it. I am.
For more, please visit us at stanford.edu.